Okay. Today we turn to study numerical linear algebra. About numerical linear algebra, two major research areas. Yeah, two major. Yeah, let me write this down. Two major research areas. The first one is solve linear systems. Solve linear systems. Here, the linear systems are the size is very large. Now, because the computers are so powerful nowadays, the linear systems in practice, usually the size is billion unknowns. Okay. The second major research area is find eigenvalues or find eigenvalues and eigenvectors. We call them eigenpairs. Find eigenpairs of a matrix. Also, the matrix, the size is huge. Now today, we first study how people find eigenvalues and eigenvectors in practice. This section is the section 9.5 in the book that I sent you by email yesterday. Okay. The first method is power method. This method look for one eigenvalue. The eigenvalue is the largest eigenvalue in magnitude. Take a review about what are eigenvalues and eigenvectors. Take a review first. Okay. Here, definition. Let A be a matrix if a scalar in linear algebra, numbers usually are called scalars. Okay, if a scalar, say lambda, and a vector, non-zero vector, important. We don't consider zero as an eigenvector. Okay, eigenvector must be non-zero. If a scalar and a vector satisfy A times B is equal to lambda times B, then lambda is an eigenvalue and the vector V an eigenvector associated with the eigenvalue lambda or eigenvector corresponding to the eigenvalue lambda. This is the definition. Okay. Then theoretically, how to find eigenvalues and eigenvector based on the following theorem. Okay, theorem. A scalar lambda 0 is an eigenvalue of a matrix A if and only if lambda 0 is a solution of the following equation. The following equation, we give a name. We call the following equation characteristic equation. Okay. Characteristic equation. The equation is A minus lambda times identity matrix. Then take determinant. If you expand this determinant by cofactor expansion formulas, then you will see that this determinant is a polynomial. And the degree depends on the size of A. Say if A, the size is n by n, then this polynomial, the degree is n. Degree is n, then there are how many zeros? N zeros. So each n by n matrix has n eigenvalues. Okay. How to find eigenvalues? Solve this equation. This equation is called characteristic equation. Okay. Solve this equation for the n zeros. Then those zeros are the eigenvalues, all the eigenvalues of the matrix A. This is from linear algebra. Okay. Theoretically, we find eigenvalues in this way. But computationally, numerically, to find eigenvalues in this way is hopelessly inefficient. As I remember, at the beginning of the semester, I remember in the second class, I showed you one example about computing a 20 by 20 determinant by using a supercomputer. Do you remember the example? 20 by 20 determinant by a supercomputer. I compute the 20 by 20 determinant by expansion. Expand the determinant with cofactor expansion formulas. How long? You remember that? How long we need to wait? We need to wait 7 years to get the result. Only 20 by 20 determinant. Now, in practice, matrix, the size is huge, right? For eigenvalue problems, size at least million by million. For linear systems, the size billion by billion unknowns. So if you still use this theoretical approach to find eigenvalues, it is hopelessly inefficient. So we need completely new idea to find eigenvalues. Completely different idea to find eigenvalues. Okay. Now this section present two basic methods to find eigenvalues. One is the power method. This method only for a single eigenvalue. Find a single eigenvalue. The eigenvalue in absolute value, the largest. The second method in this section is called QR factorization method. This method find all the eigenvalues of the matrix A simultaneously. Okay, I present these two methods. Okay, these two methods covered in this section. Okay, okay. Now, before I present the power method, let me make some assumptions on the matrix A. Okay, yeah, some assumptions. We assume for simplicity, because in this course we learn basic ideas. Okay, we don't learn, advanced algorithms. Okay, assume number one, the matrix A is a real matrix. All the entries in A are real numbers. Okay, we don't consider complex entries in matrix A. And A is a real matrix and has, suppose, n linearly independent eigenvectors. Say psi 1, psi 2, and psi n. So the eigenvectors of this matrix form a basis. Yeah, they form a basis for Rn, right? N vectors linearly independent, then it's a basis for Rn. Eigenvectors, then their corresponding eigenvalues. The corresponding eigenvalues are lambda 1 corresponding to psi 1, lambda 2, and lambda n. Okay, yeah. This is a assumption. Okay, why we call this is assumption? Because in general, a matrix A first may not have n eigenvectors. The number of eigenvectors can be less than n possible. So in general, a matrix A may not have n linearly independent eigenvectors. Now I assume this matrix A has n linearly independent eigenvectors. Right? Number two. Second assumption. Okay. All the eigenvalues now I assume them, I denote them by lambda 1, lambda 2, lambda n. All eigenvalues are real numbers. In general, this is not true. Okay, a matrix, its eigenvalues are usually complex numbers. But now, for simplicity, I assume them all are real. And also satisfy, okay, lambda 1. This eigenvalue is the largest in absolute value. Absolute value. Yeah, this guy greater than all other eigenvalues. Okay, I from 2, 3 to n. Okay. We call because of this inequality, we call this guy the dominant eigenvalue. Dominant eigenvalue. And the corresponding eigenvector, we call it dominant eigenvector. Yeah. So these two assumptions make the matrix A very special, very special. How about general A? We have advanced algorithms to handle general matrix A. But in this course, we only study basic ideas, right? We just want to see how people find eigenvalues and eigenvectors. So I make these assumptions, okay? In practice, usually the matrix A don't have these assumptions, okay? And then the power method today. The power method is a method looking for lambda 1 and psi 1, okay? See how the method works, okay? Now, how the method works? Arbitrarily pick a vector, okay? Pick a vector, V. This is in RN, okay? Okay, then define the following iteration passes. Define Vk to be A times V k minus 1. Okay. Where when k is 1, the right side V0. What is V0? V0 is vector V. Is vector V. Yeah, this vector V. Okay. Then it can be seen. It can be seen very easily. Okay. Vk is a power ak times V0. V0 is the vector V. The vector V. Vector V. How to see this? How to see this? Easy, right? Because Vk by definition is a Vk minus 1. But Vk minus 1 is equal to A times Vk minus 2. So we get A squared Vk minus 2. Then Vk minus 2 is A times Vk minus 3. So we have A to the third Vk minus 3, right? And then apply this equation again and again. We have this equation. Okay, we have this equation. Okay, now I use the first assumption. Okay, the eigenvectors, they form a basis for Rn. Therefore, I can write the vector V as a linear combination of the eigenvectors. Okay, so write V as C1, some number, okay, times eigenvector psi 1 plus C2, eigenvector psi 2, and so on. And so on, right? And so on. Right. Then, what is Vk by this equation? Vk is A times V, AK times V. So it is a C1 AK psi 1 plus C2 AK psi 2 and Cn AK psi n, okay, psi n. Okay. The psi vectors are eigenvectors, right? Say psi 1 is lambda 1 psi 1. So I repeatedly apply this equation, then I get the first term is C1 lambda k times psi 1. Similarly, the second term AK times psi 2. Psi 2 is eigenvector, so it is a lambda k psi 2 and so on. Lambda k psi n, right? Psi n. Okay, now let me take lambda 1k out. Then we have lambda 1k times C1 psi 1. And the second term becomes C2. This is a lambda 2. This is a lambda n, okay? It is a lambda 2 over lambda 1. Then k psi 2 plus Cn lambda n over lambda 1 k psi n, right? Psi n. Right. Now, by assumption number 2, lambda 1 dominate eigenvalue. So from this equation, we can have lambda I over lambda 1 in absolute value less than 1, right? Less than 1. Right? So here, this number, this ratio in absolute value less than 1. This ratio less than 1 in absolute value. So when k is large, do you agree? This expression roughly is a lambda k, lambda 1 here, lambda 1 k times C1 times psi 1. Because when k is large, the coefficients of psi 2, psi 3 to psi n, they are very small. So this term dominates the other terms. So when k is very large, we have this approximation. Yeah. Psi 1 is an eigenvector multiplied by numbers. Yeah, this is a number, right? C1 is a number. Lambda 1 is a number. A number times an eigenvector is still an eigenvector. How to see this? Yeah, how to see this? Yeah. V is an eigenvector. Multiply V by any number. This guy is still an eigenvector. How? Because A times C times V is equal to C times A V. V is an eigenvector, so lambda V. Okay. Now, let me rewrite this as a lambda times CV. So C times V is still an eigenvector associated with the eigenvalue lambda. So any scalar multiple of an eigenvector is still an eigenvector. So therefore, when k is large enough, Vk roughly is a dominant eigenvector. It is an eigenvector. Okay. Yeah. How about let me give a name to VK. Let me call it iterate. Okay. VK is an iterate. So the iterate VK, when K is large, roughly is a eigenvector associated with the dominant eigenvalue lambda 1. Okay. Yeah. So this simple idea says that we can find dominant eigenvector by multiply A by the power by multiply the vector V by a power of the matrix A. Okay. Yeah. Okay, now we solved the problem about finding eigenvector, dominant eigenvector. Then how to find the dominant eigenvalue, lambda 1. To find lambda 1, we can do that in this way. Okay. How to find? Okay. From the previous argument, we see that VK roughly is C1 lambda 1 K times psi 1. Psi 1. Okay. Yeah. Here. Yeah. Here. When K is large enough. Yeah. K much greater than 0. Yeah. Okay. How to recover from this approximation? How to recover lambda 1, the dominant eigenvalue? We can do that in this way. Okay. Okay. Consider. Okay. A vector now has n entries. Consider one entry. Say, consider the entry, the ith entry. Yeah. How about let me use this notation to denote the ith entry. Yeah. V is a vector. I use this notation to mean the ith entry of the vector V. Okay. Okay, now consider the ith entry. I can be any integer between 1 and n because the length is n. So it is roughly is C1 lambda k lambda 1 to k. Then this eigenvector, the ith entry. Okay, now I take a ratio of the iterate Vk and the previous iterate Vk minus 1. Okay, now this ratio Vk, the ith entry over the previous iterate Vk minus 1. The ith entry is approximately not equal. Roughly is Ck, C1, lambda 1 K, psi 1, I, then over, okay, now K minus 1. So C1, lambda 1 K minus 1. I. So cancel C1, cancel the ith entry of the vector psi 1. Then we have, and also cancel lambda K minus 1. Then lambda 1. So how to get lambda 1? Say consider the ith entry, the current iterate over the ith entry of the previous iterate. Then when k is large enough, the ratio roughly is lambda 1. Okay, so this is the first algorithm. Okay, algorithm 1. Okay, how to this algorithm is the power method. The power method. Yeah, this method only looking for dominant eigenvalues, dominant eigenvalue, and its eigenvector. Okay. Okay. Step 1 is take a vector. Take a vector. Okay. Then step 2. For k from 1 to 3 and so on until eigenvector and eigenvalue they converge. Okay, then stop. Okay, for k from 1 to 3 and so on. Okay, okay. Now compare vk is equal to a times v k minus 1. Okay, so here set v0. When k is 1, then the right side v0. V0 to be v. Okay. Okay, then this vk will approach to the dominant eigenvector. And for eigenvalues, and also eigenvalue, okay, take I such that pick this I, okay, such that I is between 1 and n, okay, for the computation of the dominant eigenvalue. Okay, then compute this v k the ith entry over v k minus 1. The ith entry. Okay. Let me call this number, give a name to this ratio. Say lambda k. Lambda k. Yeah. Then put an n. This n, and this follow, and this follow. Okay. Yeah. So this is the power method. The most basic power method. This method looking for dominant eigenvalues and dominant eigenvectors. Yeah, let me show you one example about this method. Yeah? Take a look at this example. Yeah. Example. Consider this matrix. Negative 1, 2, 2. This matrix, the exact eigenvalues and eigenvectors are the exact eigenpair. Okay. 3 is the eigenvalue, and corresponding eigenvector is 1, negative 1, 3. The second eigenvalue is negative 2, psi 2 eigenvector. 0, 1, negative 1. The third eigenvalue is 1, psi 3. Okay. Yeah. For this matrix, dominant eigenvalue is number 3. In absolute value, number 3 is the largest. And this eigenvector is dominant eigenvector. Now, I apply this power method Okay, to compute eigenvalue free and eigenvector psi 1. Let me tabulate the computational results in the following table. Yeah, following table. Yeah. I need to pick an initial vector V. Let me pick the vector V be 1, 0, 0. So when k is 0, k is 0. So V0 is this vector V. It is 1, 0, 0, the free entries of this vector. And the last column is lambda k. Okay. So when k is 0, we haven't started to compute lambda yet. So okay. When k is 1, multiply V0 by the matrix A. Then we get level 1, free. Then this guy is level 1. I also need to pick I. Okay. I is between 1 and n for the computation of eigenvalue. Yeah, I here, the ith entry. In this example, I pick V is this vector, I to be 1. That means that I use the first entry, the ratio of the first entry of the successive iterates to compute eigenvalue. Okay, I is 1. Okay. So I is 1. That means that negative 1, the first entry, over 1. So negative 1. Then 2. The k is 2. Negative 7, 11, 27. Then the ratio of the first entries of the successive iterates are negative 7 over negative 1. So 7 here, 7. And so on. Okay. When k is 11, then 1 is the vector vk. The first entry are very large. First entry. Why? First entry is large. Look at what is vk. This is a vk. Vk is vk is about here. Now lambda 1 is free to the k times psi 1, because free greater than 1, so free to the k increase exponentially, so very large. Okay, so that's why when k is 11, vk is a big vector. The second entry is 175, 097. Then this is a negative 5, 2, 9, 3, 8, 9. And lambda. But lambda is very close to the number 3, 3.0001. Because lambda k is a ratio of the current iterates over the previous iterates. So large number over a large number. Possible, a small number. It is free, okay, very close to free. Okay, now iteration number 12. This is a negative 5, 3, 1, 4, 3, 9. 5, 3, 5, 5, 3, 5. And this is a negative 1, 5, 9, 8, 4, 5. Okay, now eigenvalues is almost exact, very close to 3. So this first version of the power method, eigenvalues converge to the dominant eigenvalue very well, okay? But the eigenvector, because eigenvalue greater than 1, exponentially increase to infinity. But a number times eigenvector, still eigenvector. So this eigenvector, this vector, even though the entries are large, but it is still an eigenvector associated with the number 3. But the problem is, but the problem is because the entries of this vector is blows up to infinity very, very fast. It is possible that before eigenvalue converge to the number 3, we have to stop the algorithm because a computer cannot store 2 big numbers. We have to stop. In the case, we call the case, the algorithm is overflow. We have to stop. Yeah. In this example, dominate eigenvalue greater than 0. If the dominate eigenvalue less than 1, yeah, here is greater than 1. So entries increase very, very fast. But if the eigenvalue less than 1, then entries of vector vk will decrease exponentially to 0. The case is not a good case, right? In the case, we say that the algorithm underflow. Overflow, underflow, not good for in computation. Okay, in computation, yeah. So, but this is the first version. Then how to make improve on the power method. Okay, now the second version. Okay, improve the first version. Okay, the second version. The basic idea is how to improve. We normalize the vectors. Say psi 1, this vector, let's normalize it, make it into a unit vector. What it means, unit vector? This vector divided by its long. Long here, usually too long. Do you remember how to define too long? A vector, too long. It is a square root, first entry square, second entry square, and make a sum, right? Too long. Or you can use an infinite long. What it means, infinite long? A vector, infinite long is the maximum. Okay, take absolute value on the entries of the vector. Vi, by Vi, I mean the ith entry of vector V. Take absolute value on all the entries of vector V. Then pick the largest one. Yeah, the largest. Yeah, the maximum of the absolute values of the entries is called infinite long. So this long can be too long, can be infinite long, or can be any vector long. Okay, but anyway, the idea is make the vector into a unit vector and also make VK into a unit vector. Yeah, divided by its log. Yeah. So in this way, we can keep the entries of the vector VK. Okay, not big, not small, right? Not big, not small. So this is the idea to improve this first version of power method. Okay, now the second method then will be the second version of the power method. Let me present the second version in next class. Yeah. So numerically, we don't compute eigenvalues and eigenvectors through characteristic polynomials. Okay. So we need completely new idea to find eigenvalues and eigenvectors. Okay, let me stop here.